Okay, welcome back to Math 10C. We are going to continue on with our Unit G on relationships and functions. So today we're going to really focus on relationships between two quantities, and we're going to be looking at interpreting what those relations are, explaining them, are they given to us as data, as a graph, as a situation, etc. Okay, so this is one of the main objectives in Math 10C and any of the other maths leading up to, grade 11 and 12 as well. Okay, so we're on page 399. All right, and let's get going. So, relations. Much of math involves the search for patterns and relationships between data. So the search for patterns and relationships between sets of data. So if it's a, table of values that the data is given to us as, or ordered pairs, okay, or maybe it's an equation itself, okay. And of course, the reason why we do this, there are many real-life applications of math that look at the relationship between two quantities. So even if you're going to, you're heading to Edmonton and you want to know the relationship between the time it takes you and how fast you travel. Okay, here are some other examples. So the value of a computer related to how old it is. Okay, the price of a watermelon related to its weight. Or the time taken for a person to walk to school related to the distance being walked. So the two things, the relations, the value and age, we've got price and weight, and then time and distance. So in science, the speed of something, or its velocity, you'll learn is equal to the distance that you travel per unit of time. Okay, so then that's a relationship there. So if your velocity stays the same, so we'll say it stays equal, but you increase your distance, okay, well then it's going to take you more time. Okay, or if you decrease, etc. Okay, or if you increase your velocity, okay, you're still going to go the same distance. This distance isn't going to change. But if you increase your velocity, well, then that's going to decrease the time it takes you to travel somewhere. Okay? And vice versa. If you decrease your velocity, well, then it's going to increase the time it takes you to go somewhere. So the world is full of these types of relationships. Science, obviously, is a big place there. You'll talk more about relationships in science class. But for now in math, you just need to know that the definition for a relation, it is a comparison between two sets of elements. Okay, and the types of elements that we are going to be talking about, just generally speaking, are x and y, so our independent and dependent variables. Okay, variables. Okay, so one more example of a relation. So we could use the, if you guys, anybody has a job, so the amount of money earned working. Okay, and that's related to how many hours you work. Okay, so you might have an hourly wage of $16 per hour. So that money and the amount that you're making, that's the relationship there. Okay, so if you were to, work 2 hours, okay, well then you would earn $32, stuff like that. Okay, simple but still function. All right, representing the relationship between two quantities. So we're going to look at 7 different ways in which a relationship can be represented. Okay, so 7 ways that a relationship can be represented. Okay, and so here are some of the ways that are familiar to us. Okay, so we could use words. So right up here, number of hours working, that's words. Okay, we could use a mapping diagram. So you would map, like if you had the 1, 2, 3 hours, okay, that would map to, 16, map to 32, map to, etc., okay, 48. So that's one, and we'll look at another example of that. Function notation, so more on that, specifically in lessons 8, 9, 10. A table of values, and just a little reminder that whenever your table of values, x, or your independent variable, is always first, okay, even if it's horizontally. An equation itself, a set of ordered pairs, which once again, x always comes first. Okay, and then a graph. And we looked at some examples of graphs and ordered pairs yesterday. Okay, so we're going to use the following relation as an example. This one right here. Okay, so consider the following relationship. So this is just our investigation to see how some of these relations work. Okay, and the cost C, and it's given to us in cents per kilometer, of driving a car is related to the speed. Okay, just gotta get my other. So cost C is related to speed S, okay, kilometers per hour at which it is driven. So we're going to use this relation to introduce some ideas that will be developed throughout the course, and the whole point of this is to represent the relation. Okay, so we were given two variables, C and S. Okay. In the statement, the cost is going to depend on the speed, because it says the cost of driving the car is related to the speed at which it's driven. Okay? So then, if the cost depends on the speed, we would call C the dependent variable. Okay? Which would make S the independent variable. Okay? And then if we're talking about graphing this, okay, X and Y, independent is always on your horizontal, dependent is on your vertical. So I'm just going to put an X and a Y there because we're used to seeing X's and Y's, but we just need to know, we're interpreting this and we're applying it to our knowledge of just the coordinate plane. So if I'm saying S is independent, okay, well, technically then my S is there and my C is there. Okay? So, when representing a relation, we often regard the values of the independent variable as the input. Independent input. Okay, so remember that. Independent input. And then the values of the dependent variable are the output. Dependent out. Okay. So before considering how to represent this relation, we need data. Okay? So we need those output and input values. Another important thing, so the input is also going to be the domain. Okay? And the output is the range. So things that we've talked about so far is, I'm just going to grab a sticky note. So you can draw or make this note wherever you want. Okay, I'm just going to move this to the side. So for variables that we've talked about so far, okay, we've got the X variable and the Y variable. Okay, X is the independent variable, Y is the dependent. X is the input, Y is the output, in. Okay. The X value has to do with our domain. So anytime we talk about domain, we're talking about the X, all the X's that can happen. Okay, and if we're talking about all the Y's that can happen, that's our range. Okay, so far we might add to this, but for now that's kind of our summary of the variables. Okay, and we'll talk more about that later. Okay. So, page 400, we've done a lot of math. Okay, so obviously we would not attempt to collect data for every possible input value, so every possible speed, because it would be continuous, right? Remember we talked about continuous versus discrete. Okay, so then it would make more sense for us to use input values you know, starting at a certain amount and then just increasing by, say, 10 kilometers per hour. Okay, so we're going to choose input values of speeds 20 to 120 kilometers, and we're going to increase by 10 kilometers per hour each time. Okay, and then that's going to match with some output values that we're going to look at in these diagrams. So the diagrams show how the information collected can be represented. Okay, these are all, I'm going to highlight that. Diagrams show how the information can be represented. We've got ordered pairs, table of values, mapping diagram. And then, of course, the ordered pairs themselves can be plotted in a graph. Okay, so these are all the examples. So there's my input of 20 to 120, and there's my cost. Okay, I've got my ordered pairs there. Okay, if I take my table of values, I put them into the ordered pairs, I graph them. So that's the relationship there. And once again, remember, these are always x, y, x, y. This is my x, this is my y. So those are the general, there's so many general rules in math, but we just need to take the information given to us and apply them to the general rules that we know. Okay, and then so you'll see here, okay, we've got this we would call that a parabola. Okay, so if we look at 10 right here, we see that it costs us 10 cents per kilometer if we go 20, and if we go 120 kilometers per hour. So then it makes sense here with our mapping diagram that there's more than one S. So for example, if I highlight the 20 and the 120 are both going to 10. Okay? But we do see that there's only one S for all of those. Okay? Or sorry, only one C for all of these. So 20 only has one C. C can have more than one S, but S, not the other way around. Okay, so those are all the different ways that we can represent the information and the relationship. Okay, next one. So, we have only chosen some possible input values because we said, it wouldn't be time effective to put all of them down. But if we did, okay, it would make sense to fill in all these little spaces, okay? Of course, you don't just jump from 20 to 40 kilometers per hour. You go at little increments there, right? It's continuous data, okay? So we can say, straighten this out, it is continuous data. So then we can actually fill this in here. Okay, so we can connect the dots in a nice smooth line that represents the overall trend. Okay? Okay, so that's what it says right here. It makes sense to connect the points on the graph in some way. So later we're going to learn how this is done and how we can make an equation. For now, though, the equation is just given to us. So you could actually, with the Inspires and the 83s, you put those data points in, and then you can actually come up with this equation, which is called regressions. But for now, we're just looking at the kind of the big ideas. Okay, so the graph and equation for the relation is given below. And this equation is only valid for certain input values, which make up the domain of the relation. So once again, remember, domain, okay, is going to be here. Domain are all my x values. Whereas my range, that's my cost. Okay, so for example, the equation wouldn't be valid for a speed of 5,000. Okay, because it's not normal to drive to Edmonton at 5,000 kilometers per hour. We would have to tweak our Fords a little bit. Okay, so here is the equation and the graph. Okay, those S's are representing these data points. This C is representing these data points. All right. So now we're going to talk more about those independent and dependent variables in the relationship. So the values of the independent variable represents the input, in, and then the dependent are the outputs. Okay, and then in ordered pair, we've already talked about this. Okay, this, oh, my computer fell asleep. Wake up, computer. Come on, computer. Please wake up. Yeah, there we go. Okay, so there's my independent, and that's my dependent. Okay, so the value of the first coordinate, independent. Second coordinate, dependent. Always going to be true. In a table of values, same thing. If I have a table of values, I've talked about this, x, y, and then all those data points. Or if it's on the side, sometimes you'll have a horizontal one, but same thing, x is always first. Okay, and that's the independent. On a mapping diagram, okay, so that's the x to y, okay, so it'll map across, and sometimes, oops, why did I do that? One across there, okay, and then maybe one from here will map up to the same one. Okay, on a graph, the independent will be on the horizontal axis. Okay, horizontal right here on the x-axis, dependent right here. And then in an equation, we always isolate, or we try to isolate the dependent variable on the left side. So we're going to talk, here's an equation here. So there's my dependent, there's my independent. Okay, so this is the example that we're going to look at for right here. Okay, so dependent variable, output, second coordinate, vertical axis. X is the independent, which is the input, and the first coordinate on the horizontal axis. Okay, so definitely some repetition here for good reason. We are going to talk about this for the next couple of years, so makes it super awesome if you can just, you know, get that base learning super solid for all the linear, quadratic, cubic, sinusoidal relations that we are going to do. Okay, so some of those words maybe you didn't know what that meant, but they're all relations and functions. Okay? All right. So now we're going to do a couple of examples. So the diagram shows relations expressed in different ways. So we've got our mapping notation, our table of our table of values, and our coordinate points. Okay, so then we're going to state the independent variable. We're going to state the dependent, inputs, outputs. Okay, so I know that my independent variable is my x, and it is my input. I know that my y is my dependent, and it is my output. I also know that x always comes first, and my dependent, my y, goes second. So then that means that this is my x. My independent variable, okay, is going to be p. All right, how do I want to do this? Show relations. How about for here, I'll just so independent variable is p. That means that there's my dependent variable is q. My input is also p. So I'm just going to go like this, p. And then my output is q. Okay, and oh, it says list the input. So all my p values are going to be 5, 8, 11. And then all my q values, 10 and 16. Okay, so state the variable, list the inputs. So we'll do the same thing over here. Okay, whoop. So my independent variable, my first one, so it's going to be v, which means my dependent is a. Listing my inputs, that's going to be 4, 10, and 25. And listing my outputs, 15, 12, 15. Okay, and then up here, okay, same thing. My independent variable, so my coordinate points here, So normally it would be x and y. So B is first, C is second. Okay, listing my inputs. Okay, well, my inputs, I'm going to highlight all the first terms. Those are going to be all my inputs. So 3, 4, 5, and 6. Now highlighting my outputs, that's going to be 7, 11, 15, 19. 7, 11, 7, 11. Okay, 15, 19. Easy peasy. Okay, so as long as you've got this committed to memory, answering questions like this is not bad. Okay, so up here I had mapping notation, a table of values and coordinate points. Now I'm going to look at an equation and a graph. So just a different way to show a relationship. Okay, so for I, it says state the independent variable and then state the dependent variable. Okay. So for this first one, the independent variable, okay, is going to be r. Okay. 2 and pi are constants. Okay. Constant. So I would also, I guess, consider them my coefficients. My r, that is the variable. So variable itself, remember, means it can change, right? R could equal 1 or 2 or 3 or 4. Well, 2 is always equal to 2, and pi is always equal to 3.1415926, blah, 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 whatever else is next. Okay? So that is my variable, my independent variable. And then my dependent, that's the one that's on the left. So that's going to be C. Okay? For B, I've got a graph. Okay, well, I know that I would just put those x, y. I know that that is independent. That is dependent. So that means that my independent is going to be time. Okay, in T. And then my dependent is going to be height, which would be H. All right. Oh, and I've got a word statement here. So another way that we can represent information. So now since it says the amount of sap S, okay, so that's one variable, obtained from a maple tree is dependent on the time, okay, here, and it's dependent on, that's important. Okay, but there's our second variable. Okay, a container is left attached to the maple tree. So the amount of sap obtained from a maple tree is dependent on the time. Okay, so looking for my independent and my dependent. Okay, well, it says that sap is dependent. Okay, so the sap is dependent, which means time is independent. Okay, and so the thing is, in science and math, a heck of a lot of the time, if you've got time, it's independent. Okay, I don't think I've seen too many examples where time was the dependent thing. Okay, so if in doubt, if it is time, it's going to be independent. Okay? All right. So if you're watching this one at home or what have you, take some time to do 1 to 4, even if it's just A, B's. Actually, I don't know if it is A's and B's. Yeah, so you could do the, A of each one or something like that. Okay, and you could pause me. Otherwise, I'm going to keep going on. And we're going to talk about plotting ordered pairs. Okay, so we've talked about independent and dependent variables. Now we're going to talk about ordered pairs specifically. Okay, so in this section, and it's still about relations. Okay, defined by an equation, and we're going to sketch a graph by plotting those ordered pairs. Okay, so this is pretty much our steps. Okay, so first, you make a table of inputs by choosing the replacements for the independent variable. Okay, so whatever our x is. Okay. So if we've got an equation, we would say, you know, like 1, 2, 3 or whatever it is going to be, and then we plug those into our equation to get our y's. Okay, which is what it's saying in this step. For each independent variable value, calculate the corresponding value of the dependent variable, and then plot those ordered pairs on the Cartesian plane or the coordinate plane. Okay, so those are the instructions that we're going to follow, and then here is our example. So here's our relationship that we're going to be dealing with. Y is equal to 2x minus 5. So y is equal to, whenever x doubles, minus 5. So we're going to complete the first 5 rows of the following table that shows some of these possible input values. Okay, so we're given the values here. We see that as we go down here, so we're increasing by 1, starting at -2. So if I were to plug in, okay, all I would do, I would start off, this is how I would do it. So I'm putting in -2 for x. So this is going to be, okay, 2, there's this 2. Okay, now x is -2. So I'm going to plug it in. Okay, and then that -5 stays the same. So 2 times -2 is -4. -4 minus 5 is -9. Okay, and so then there's my ordered pair, -2, -9. Okay, next one. So now I've got -1 that I'm going to plug in here. So 2 times -1 is -2. Oh, why did I write that? -2 subtract 5 is -7. Okay, so then -7, -2. Oh, crikey, you can tell it's time to go home. -1, -7. Okay, moving on. 2 times 0, so no matter what you are, if you're multiplied by 0, you're also 0. And then 0 minus 5 is -5. So -5, 0, -5. Now we can see a bit of a pattern here, right? We're increasing by 2 each time. We started as more negative and we're becoming less negative. Okay, so a person could, if you see this pattern here, you could skip ahead and fill in the rest, but because we're really focusing on this input-output thing, because here's my input, here's my output. Output, and then if I can draw a little input. So 2 times 1 is 2. 2 subtract 5 is -3. Two times 2 is 4. Subtract 5 is -1. Okay. So we completed the first 5 rows. Done. Okay. So then it says plot the ordered pairs on the grid provided. Okay, so you just have to take these points, so -2 and 9. Okay, starting at my origin, I go -2, and then -9 is going to go all the way down here. Okay. -2, -9. Next is -1, -7, 0 and -5, 1 and -3, 2 and -1. Okay, and that's it. Okay, so plot the ordered pairs. Done. Connect the points on a grid. So we would definitely want to use a ruler, which I don't. Okay, this is kind of crazy. It's just a mirror, but okay, we want to use that ruler and we want to make sure that it's lined up to the best possible trend line. Okay. That's why those clear rulers are so good, because then you can put them kind of perfectly there. Okay, so we connected the points and we extended the lines in both directions, and then it says put arrows at both ends. Okay, so those arrows, as you can imagine, are indicating that this line is going to continue on. And if I was actually drawing this, I would have moved that over after I erased it. But because I'm using pink pen, we'll just pretend that that's going right through that. Okay, use the graph to determine the value of y when x is equal to 6. Okay, so reading off my x's, x is equal to 6 right here. So then I just have to go up to there, and then I read over to there. Okay, so when x is equal to 6, I've got a value of 7. Okay, so then I can write that 6, 7, 6, 7. Okay. For E, use the equation to determine the value of y when x is equal to 6. Okay, well my equation, I'm just going to rewrite it down from up there. Okay, so I would plug in that 6 for x. 2 times 6 is 12. 12 subtract 5 is 7. So when when x is equal to 6, y is equal to 7, which is right there. So that's our coordinate point. Okay. Write the value of y into the table of values. Okay, well I guess we got ahead of ourselves. Use the graph to determine the value of x. So now we're going backwards when y is equal to 3. Okay, so same idea. It's just that now I go to where's y equal to 3, which is going to be right there. And I trace it over, and I come down. And that's going to be equal to 4. Okay? So then if y is 3 when x is 4. So make sure you don't get those mixed up. Okay, so then there's our plotted point. Okay. Okay, and then complete the following statement. This relationship is called a linear relationship. Okay, as in line. Okay, because it is a straight line. And in grade 10, we focus almost purely on linear relationships. Okay, so any shape like that, it could be going the other way. Technically, it could be going straight up or straight across horizontally. In grade 11, the focus is on, we would call it a quadratic. So all that factoring that we've been doing, okay, so like y is equal to x squared plus 2x plus 1, okay, that is a quadratic. Oh, computer fell asleep again. All right, there we go. Okay, that's a quadratic, and that's grade 11. Okay, so that's 20 level 20-1, 20-2 math. Here, we're just dealing with the linear relationships. Okay, so one more example. Okay, and it's going to be not a linear relationship, so we're going to go a little bit into this, but the point of it is to see how it's still going to be a lot similar with the input, outputs, etc. Okay, so this is our data, our equation. We've got our data in the table. Sorry, I'm trying to just sharpen this a little bit. The focus is hard to get. So there's all my inputs, and it's my x. I'm going to calculate the outputs, put my ordered pair, plot it. We're going to talk about symmetry, and same thing, we're going to find the different points, given to us. Okay, so I start out by writing my formula, okay, and then I just take turns going all the way down here, substituting in. So first one, I put a 4 in. So 4 squared is 16. 16 minus 6 is 10. Okay. Next one is 3. 3 squared is 9. 9 minus 6 is 3. Okay. 2 squared is 4. 4 minus 6. Okay, so now I'm into the negatives. Negative 2. 1 squared is just 1. 1 subtract 6 is minus 5. Okay, and we would just continue on, okay, going all the way down. So 0 subtract 6, negative 6. And then look at what happens here, okay? So now this is why it's important to use brackets, because remember, if we have negative 1 squared, if you put that into your calculator, it's going to give you negative 1. Okay, we need to put the brackets around because the entire thing is squared. So negative 1 squared is equal to positive 1 because negative 1 times negative 1 is 1. Okay? Okay, so then 1 subtract 5. So now we're back to negative 5 again. I'm just going to continue on up here. Negative 2, so same idea. I'm going to make sure that I was going to say put it into my brackets, but I can be doing this with mental math. Negative 2 squared is 4. 4 subtract 6 is going to be negative 2 again. Okay, and you'll notice, right, it doesn't, because I'm squaring it, they're going to be the same. So this next one is going to be 3. Next one's going to be 10. Okay, so negative 3 squared is 9. 9 subtract 6 is still going to be 3. Negative 14 squared is positive 16. Positive 16 subtract 6 is 10. Okay, so then we can fill out the rest of this graph right here, or table of values rather. All right. That blue sure doesn't show up very well. Let's go back to pink. Okay, so there is the table of values. So we were given an equation, we were given our input values, and then we filled out the output and our ordered pairs. So one of the main reasons to do this is to graph it. Okay, so if we plot the ordered pairs in the grid, okay, so just take some time to plot those right now, and I'll plot mine. Okay, so you'll notice once you get down to the the y axis right here, or x is equal to 0, you're going to come back up again. And it's going to be what we call symmetrical. So if you were to put a mirror down there, it would look exactly the same, both sides. Okay, like that. Okay, so it looks the same. So we say it's symmetrical. Okay, so we plotted the ordered pairs. Use the symmetry of the graph or table to predict the value. So we did that because we talked about how those started to repeat. Okay. Use the equation to determine the value of y when x is equal to negative 4. Okay, so looking at this graph, we still have to ask ourselves, okay, does it make sense to do this continuously? And yes, it does. Okay, there's no like, I mean, sometimes there might be a word problem where no, it would be discrete, but it would be a specific example. Okay, so we would do that, and then we would be able to say, okay, when x is equal to negative 4, so x is equal to negative 4 right here. So then I would go up. I'll do this in a different color, in orange. I'll go up, okay, and there's my negative 10, okay. I did that with the graph, which that's good to prove there too. It did say to use the equation, but once again, we already did that up there, okay. So we predicted and we did the equation, and we showed on the graph that it's true, okay, and we wrote that in the space. And we connected the points, okay? And then this seems like a really obvious question, because it is. Why do you think this type of relation is called nonlinear? It's not a straight line. Graph of relation, not a straight line. Okay. And yeah, we will focus on these type mostly in grade 11, like I said, for now. Mostly linear. Okay. Okay, so you guys can complete those assignments. There is the lesson. On Tuesday, we will be going over the next part, so just make sure that you're all caught up for that. And I hope everyone had a good weekend. See ya.